Voice AI conversations feel natural only if the timing feels right. Turn detection is one of the most crucial things that makes these voice conversations feel alive. So for example, if the agent waits too long after I stop speaking, that makes me feel an awkward lag. If it decides too early that I'm done and barges in, for example, then that destroys the conversation. So turn detection is a crucial element of building a real sounding voice conversation. And the simplest way to solve this is through silence detection. Look for silence. So that gives us the basic voice activity detection or VAD approach. In an earlier video, I've talked about turn detection in isolation, silence-based versus audio-based versus text-based turn detector. At this point, many providers have started to include turn detection along with their STT or ASR speech recognition engines, and they have multiple open source implementations also available. In this video, I'll talk about how to make end-to-end voice pipelines more effective and low latency. For example, what does it take to create voice conversations with AI agents that feel interactive and live, like two humans talking? So timely turn detection is definitely a core part of it, but it also depends on the effective orchestration of turn detector along with the downstream LLM generation and the TTS modules. I'll also talk about a clever trick that allows the downstream LLM to start thinking even before the user has stopped speaking or finished the turn. That optimization or trick is essential to making the end-to-end pipeline feel like humans talking. But before that, let's overview the key ideas of semantic turn detection. The most basic turn detector uses a voice activity detection and watches the audio stream, asks, is the user speaking right now or not? When the speech stops, the system waits for a fixed threshold, say 2 seconds, and then declares the end of turn. The problem is silence does not mean the user has stopped speaking. The user might be just thinking, pausing, and detecting silence might be. Similarly, my number is 4412, and then I'm thinking about the rest of the digits. And the silence is not a good indicator of conversational completion. So how do we solve this problem? The way to approach this end of turn detection is to view it as a sequence labeling problem, to predict whether, using a machine learning model, whether the user has stopped speaking or not. So the system receives these audio chunks, and for each chunk, the model has to decide whether the turn has finished or not. The issue is that you don't just want the system to be accurate, but also low latency. So you want to detect very quickly if the user has finished speaking. Next question is, what signals should we use to predict if the user has finished her? So there are two obvious signals, the audio and the text. The audio gives you the pauses, the prosody, intonation, and so on. The text gives you the semantic context, what is actually being spoken. Interestingly, neither of them is good enough on its own. So if the user pauses in the middle of a phone number, 4412, and then pauses, the audio intonation might detect that user is done, but in fact he's pausing and thinking about a number. The text mode, the text detector will detect that the user is not done. If you're using a text-based detector, then the user might be completing sentences, but then just going to continue, but the text detector won't. And for example, this is a problem. This is the problem. Then it pauses. The words may not alone tell you whether the speaker is trailing off or about to continue. So the correct direction is to combine both the audio and the text. Audio for the timing and the intonation, prosody, text for what is being spoken. This leads to modern semantic turn detectors where the system is not just looking for silence, it's looking for audio and text signals. Modern semantic turn detectors use both audio and text classifiers. Text classifier, the LLM, which generates the response, can also act as a text classifier. Audio model detects the speech patterns, pauses, and intonation. Text model detects whether the utterance seems semantically complete. So that's a quick background on semantic turn detection. And now let's talk about a complete end-to-end architecture, which shows how a semantic turn detector is orchestrated inside an end-to-end cascaded pipeline, which includes both speech-to-text LLM and the TTS model. As I said, the LLM acts both as a turn detector, the text, as well as the response generator. This diagram is from the PipeCat documentation. This is a very nice illustration of how an end-to-end system works. So how does this work? The user audio stream is piped to two parallel system modules. One is the STT generator, which is streaming, produces streaming outputs, partial outputs. Other is VAD, followed by audio-based smart turn or detector. Both of these outputs, the partial transcript and the smart turn output, is passed to an LLM, which does two things. One is detects whether the user stopped speaking and accordingly generates the response. So both the signals pass to the LLM, and a clever move is that the LLM can start thinking or reasoning even before the user has finished speaking. So these partial responses go to the LLM, and LLM at every such instance is able to decide whether user has finished speaking and what should the response be. The response is either of these three. If the LLM detects the user is not finished speaking, then it makes a further judgment whether the user is almost going to finish or it has to wait longer. In the first case, it generates a short incomplete symbol or token, which is this empty circle. And if it assumes that the user will take longer to finish, then it generates this long incomplete token. If it detects the user has indeed finished, then it generates the actual response. So what happens is that the LLM gets time to think about the response, even when the user has not finished speaking. Now let's see why this early generation from LLM helps. Note the LLM response has to still go through the TTS engine, text-to-speech, where it will be spoken. So that adds latency. So if the system waits until the user has fully finished before even starting the LLM response, the total delay becomes noticeable. The LLM generates the delay due to that, and then TTS further. Instead, the LLM can be polled while the user is still speaking. So if the user is clearly not done, the model just emits these small signals and is finished. But if the user is done, then the model can immediately continue into the actual response. So essentially, the system is trying to think ahead. The polling is sort of a decision engine, whether the LLM can now start thinking and generate it. So this starts to look less like turn taking and more like a continuous interaction, where the LLM continuously monitors the input audio and the text and decides when to respond and presents its response right at the current moment. Why is this continuous interaction important? Humans think while others speak, whereas these traditional voice AI or text-based systems are stuck in a legacy mode where when the human and the agent take strict turns. The user speaks, the agent waits, agent thinks, agent speaks, and the user waits for it. Or can interrupt, but that's a very minor kind of. Human conversation is not really like that. Humans listen, predict, prepare, and sometimes even respond immediately when the other person finishes. So the better model of interaction is continuous. And the future of voice agents is not just better end-to-end turn detection. It is models that listen and think continuously. That's also why direct speech-to-speech models are interesting and becoming more important. Speech-to-speech systems like, for example, OpenAI real-time model or Moshi-like models. The model consumes audio continuously, updates its internal state, and decides. There's an internal decision engine which decides when to speak. It can respond when the user finishes or interrupt if the interaction calls for it. So turn detection as such is inbuilt into those speech-to-speech system. Those models have their own drawbacks. You have explicit control in these cascaded systems where the transcription and the LLM and TTS are separate, and whereas it's more of a black box for those speech-to-speech. But the advantage there is that turn detection doesn't need to be explicitly modeled. It's part of the training. To recap, there is a spectrum of models that lead us to live interactive conversations. The earliest one, or the simplest one, naive model is the VAD activity detector plus with a threshold. Then there are these semantic turn detection models that use both audio and text. Then there are these LLM assisted systems that start thinking or preparing responses before the user has finished. And finally, there are these continuous speech-to-speech models where listening, thinking, speaking are all happening in parallel. So irrespective of where you are in that spectrum, turn detection is an essential element to make the interactions sound live, more human-like. It is, whether it's explicitly modeled like here or implicit as in speech-to-speech system. It is where latency, interruption, language understanding, all of those factors meet together to give rise to a live conversation.